And you'll be glad you know it if you're taking calculus next year. So we're learning to find the derivative of a function that's implicitly defined. So we probably haven't even talked about what that is yet in math. And we're learning to find the slope of the tangent at a specific point of a function that is implicitly defined. So in the last chapter, and pretty much throughout high school, except for circles, we've always dealt with functions that were defined explicitly, where y is a function of x. So y is on this side by itself, and on this side, everything's in terms of x. That's an explicit function, where it's explicitly defined. So y is defined as a function of x. But functions can also be defined explicitly. So here we have 3xy, we don't have y by itself, equals 12. In this case, it would be easy to get y by itself and then find the derivative. But then if we get a function like this, it's way harder to get y by itself because we have a y and a y cubed, okay? So they can be defined implicitly as well as functions of x and y. And there's got to be a way to find the derivative other than trying to find really intense algebraic ways to get y by itself. So we're going to start off with our circle again, because we know what our slope of the tangent should be. And then I'll show you how implicit differentiation works so that we can get the right answer as well. So if you remember back to circles, a property of circles was that the tangent was always perpendicular to the radius at that point. So at the point 3, -4, here's our radius. And we can see that our radius, just write it under here, m radius, has a slope, and we can see it's a negative slope. It's got a rise of -4 and a run of 3. So we would know that because it's a circle, and a property of circle is that the tangent's always perpendicular to the radius, that the slope of the tangent would be +3/4. Negative reciprocal, perpendicular. So I could draw it in up 3 from this point, down 3, and this would be my tangent. At that point. So that's just a property of circles, but now we're going to do it using calculus. This is cool. So here we have our function is defined implicitly. So we have x² + y² = 25. And we're going to dive in. So we're going to take the derivative of each of these with respect to x. So if we take the derivative of x² with respect to x, we just get 2x. That's easy. Plus, so we want to take the derivative. So I'm going to use, remember, there's lots of ways to say we're finding the derivative. There's y prime, which is common. There's f prime at x. And then there's this Leibniz notation, dy by dx. That's what we're going to use for implicit differentiation in grade 12. You'll find in first years, probably about half the teachers use dy by dx when doing implicit differentiation, and the other half use y prime because it leads into something called differential equations, which is cool. But we're going to use Leibniz notation. So all I'm writing here, I haven't derived it yet, but I want to say that I'm finding the derivative of y² with respect to x. So if you're looking at this and you want to say that in your mind, I'm taking the derivative of y² with respect to x, because I'm taking the derivative of each piece with respect to x. And the derivative of a constant with respect to x is 0. So I've already taken the derivative of this. And I've already taken the derivative of this. I haven't taken the derivative of y² with respect to x yet because it involves the chain rule. So if I want to take the derivative of y squared with respect to x, it's not a, y is not in terms of x, okay? So it involves the chain rule in that first I'm going to differentiate y squared with respect to y. So that's kind of like my outer derivative. So if I take the derivative of y squared with respect to y, I get 2y, just using the power rule. But I want the derivative with respect to x. So then I have to take the inner derivative, which would be what's the derivative of y with respect to x, and that is dy by dx, which is the slope of the tangent. So I'm going to go over that again on a piece of paper here, just to show you that separately again. So you don't have to write this down, but go over it again. So one of the things we learned about the chain rule is that dy by dx is dy by du times du by dx. Okay, so if I think of derivative of y squared with respect to x, that's going to be the same as the derivative of y squared with respect to y times the derivative of y with respect to x. So you can see these guys are the same here and the same here, and that's how the chain rule works. And then the derivative of y squared with respect to y, so this whole thing is 2y times the derivative of y with respect to x. And when you're multiplying, you can just write them side by side. So 2y dy dx. But it's really important to remember that dy by dx is the slope of the tangent, or the derivative, which is what we're looking for. Okay, so this is just the definition of the plane chain rule, and now we're applying it to deriving something that's in terms of y with respect to x, implicitly. All right, so once you've done that, your job is to get the slope of the tangent dy by dx by itself. So if I want to get this by itself, remember these guys are multiplying together. So my first step would be to subtract 2x on both sides. So on this side, I've got 2y times dy by dx. And on this side, I've got negative 2x. And now I'm going to divide both sides by 2y to get dy by dx by itself, because that's the slope of the tangent, or the derivative. So these divide out. The 2's divide out. With implicit differentiation, we're not as concerned with simplifying our form as we are with just getting an expression for the slope of the tangent. So that means the slope of the tangent, so this side means slope of the tangent, is negative x over y. So we can take this point they gave us up here in the question, because they want the slope of the tangent at the point 3, negative 4, meaning at the point where x is 3 and y is negative 4. So you can write, this is a thing where you write dy by dx at 3, negative 4 is equal to negative 3, because x is 3, over y is negative 4. The two negatives divide out, and therefore the slope of the tangent at 3, negative 4 is positive 3/4. Or I always like to then do m tangent. So I'm showing that I know it represents the slope of the tangent is 3/4, which is the same as what we got when we just used the property of circles, that the tangent is perpendicular to the radius at the point. So that's kind of like the fundamental idea behind implicit differentiation. And we're just going to try a bunch of questions now. Ones where we have to use the product rule, etc. And it gets, by the end of it, I think you'll find it easy by the end of the lesson. You'll have caught on. Okay, so again, what is the derivative of 3y squared with respect to x? Use the chain rule. Okay, so we're thinking, what is the derivative of 3y squared with respect to x? Okay, so we can do what I did on my scrap piece of paper, which is say, well, first we're going to take the derivative of 3y squared with respect to y, and then we're going to multiply that by the derivative of y with respect to x. And then derivative of 3y squared with respect to y is 6y, using the power rule. But then that's multiplied by dy by dx. So that's kind of like writing it out in long form. But what I'm hoping you're going to do is you're going to see, by the end of this lesson, you're going to be able to see 3y squared and say if I'm deriving that with respect to x, deriving it with respect to x, it's going to be 6y times the derivative of y with respect to x. Okay. So our steps for implicit differentiation. So you're still finding dy by dx, which is y prime, which is f prime at x, which is the slope of the tangent. You're still finding that. Okay, they all mean the same thing. So first step is differentiate both sides with respect to x. Use the chain rule for terms that contain y. Remember that differentiating x times y would involve the product rule because it's two functions multiplying together. Then get dy by dx by itself using algebra, i.e. You want to get the terms that have dy by dx in them if there's more than one on one side of the equation and the terms that don't have it on the other, so that you can get dy by dx by itself. All right, so our first one, differentiate implicitly. So because this is the function and now all of a sudden we're going to start deriving it, and we don't write y prime equals, I kind of put a line there just to separate this being the function from now I'm going to find the derivative below. So the derivative of x squared is 2x with respect to x. Anyone think they know what the derivative of 4y squared is with respect to x? Already.
Would it be 8y dy over dx?
Yes, it would be. Very good. So 2 times 4 is 8y. That's deriving it with respect to y. But because we're deriving it with respect to x, we have to multiply by dy by dx. Perfect. Equals, and then the derivative of any constant with respect to x is 0. So now I've got it all derived. I just want to get dy by dx by itself using algebra. So to do that, I'm going to first subtract 2x on both sides. Then divide both sides by 8y. So we get dy by dx is, you can reduce the 2 and the 8. I'm not going to deduct marks if you don't do that. For some reason, simplifying implicit differentiation questions doesn't seem to be a thing. I just kind of automatically do it especially if it's an easy simplify, but you're not required to. So that would be your answer. Y prime or dy by dx is negative x over 4y. All right, for B, so I put my line here, and then I want to differentiate it x, y, but it's a product, x times y. So up here, I'm going to make my first, second function derivative. So my first function is x, and my second function is y. And the derivative of x with respect to x is 1. The derivative of y with respect to x is dy by dx, or 1 times dy by dx, which is just dy by dx. So in order just to derive this part here, I'm going to circle it in orange and then write its derivative in orange. It's a product rule, so derivative of the first times the second, plus the first times the derivative of the second. So that orange part is just deriving x times y. And then plus the derivative of y cubed, sorry, I was getting ahead of myself. The derivative of y cubed is going to be 3y squared times dy by dx, because it involves y, equals the derivative of x squared with respect to x is 2x. The derivative of 1, which is a constant with respect to x, is 0. So this is, below we have the derivative. We've derived it all with respect to x. Now we want to get dy by dx by itself. So I can see that this term and this term both involve dy by dx. So I'm going to leave them on the left side, and I'm going to subtract y on both sides. (2x minus y) here. So does anyone have an algebraic idea for how I could get dy by dx by itself? Here's one term, here's another. What do they have in common?
dy by dx.
Yes, so we can common factor out dy by dx from each chunk here. And then in the bracket, we're going to get x plus 3y squared. So I common factored out dy by dx. And then to get dy by dx by itself, I'm going to divide each side by x plus 3y squared. So that means, therefore, dy by dx, or y prime, slope of the tangent, is equal to 2x minus y over x plus 3y squared. So the derivative is in terms of x and y as well.
Ms. Northwood?
Yep.
Is the reason we're defining these implicitly rather than like finding like an explicit definition and then finding the derivative? I guess they aren't really functions.
True. These are not functions. I'm going to show you that when we find the slope of the tangent. I've got it on my graph. But yeah, these are like ellipses, circles, then spirals, like etc. Things that don't, they don't pass the vertical line test for sure, and they're very hard to get y just in terms of x. They're much easier to write x and y together to define them. The algebra would be yucky. But you can still find, as we saw with our circle, that wasn't a function, you can still find tangents. Okay, our next one. So see 2xy minus y cubed minus 4 equals 0. So right away, I see 2xy, and I see that's going to be a product rule. So I'm going to write off to the side here. So my first function is 2x, and my second one is y. And the derivative of 2x with respect to x is 2, And the derivative of y with respect to x is dy by dx. So if I go and find the derivative now, the derivative of 2xy is going to be 2y plus 2x times dy by dx. And then minus the derivative of y cubed is 3y squared times dy by dx, because it's in terms of y. Be careful. Always remember when you're deriving something with y that you have to multiply by dy by dx. The inner derivative is dy by dx when you're using the chain rule. And then the derivative of -4 is 0, and the derivative of 0 is 0. So now we can see on the left side, we've got two terms that have dy by dx in them and one that doesn't. So we'll subtract that one over to the other side. So on this side, I'd have -2y. And I can see what I've got left here. I can common factor out dy by dx. And if I common factor it out of the first chunk or first scoop, I would have 2x. And out of the second scoop, -3y squared. And then I can divide both sides by 2x minus 3y squared. And I get that the derivative of y with respect to x, or y prime, is -2y times 2x minus 3y squared. For D, this is going to be a product rule. So see if you can set up your first second function derivative. So your first function's 3x. Your second one's y squared. Derivative of 3x with respect to x is 3. The derivative of y squared with respect to x is going to be 2y times dy by dx. And then we're going to use the product rule. So just to derive this part, it's going to be derivative of the first times the second, which is 3y squared, plus the first times the derivative of the second. So 3x times 2y times dy by dx. So 3x times 2y is actually 6xy times dy by dx. Because you can multiply the monomials together. Then it's going to be plus the derivative of y cubed with respect to x. So that's going to be 3y squared dy by dx equals, and the derivative of 8 is 0. Then we want to get the slope of the tangent part, which is this dy by dx. That's our slope of a tangent by itself. So we're going to subtract 3y squared on both sides. Common factor out dy by dx from each scoop. Divide both sides by 6xy plus 3y squared. And there's our derivative.
I'm just wondering, why would we not be able to simplify that? I guess they don't. We aren't required to.
You're not required to. You would be able to, but in generally they don't, John, because then you're also going to talk about restrictions like y can equal 0 and stuff like that. So
Okay.
they just leave you kind of in unsimplified form, because generally what the reason you're going to do this is to be able to plug in a point and find the slope of the tangent at that point.
All right.
Okay. So we're kind of just practicing going through the motions to get to the slope of the tangent. And then I've got a few questions at the end where we actually substitute in numbers to find the slope of the tangent at that point. I know it's tempting, and if you want to go ahead and simplify, that's fine. You're just not required to in this. Okay, so x cubed times y to the 4th equals 3. So hopefully you recognize that as a product rule. So our first function is x cubed, and our second one is y to the 4th. Derivative of x cubed with respect to x is 3x squared. Derivative of y to the 4th with respect to x is going to be 4y cubed times dy by dx. So derivative of the first times the second is 3x squared y to the 4th plus 4x cubed y cubed dy by dx equals 0. One of the things, most common errors, is people forget that the derivative of a constant is 0 and they put a 3 there by accident. So don't let that happen to you. And then this one's, we've only got the dy by dx in one spot anyways. So we'll leave this term on the left for now and subtract over this one to the right. Divide both sides. I know this one would be really tempting to simplify, and again, you can. It's up to you. So you can either leave it like that, or if it's just bugging you, you can say it's negative 3y over 4x. You can see you have an x squared in the numerator and x cubed in the denominator. So you'd end up just with an x in the denominator. Same with a y fourth in the numerator and a y cubed in the denominator. You can use exponent rules to get it to negative 3y over 4x. Okay, so hopefully you're getting the hang of implicit differentiation. So we'll try one where we're subbing in a number now. And I've also put that one on Desmos so we can see a picture of it. So find the slope of the tangent to the curve 2x squared plus 3y squared equals 5 at the point 1, 1. So slope of the tangent means find dy by dx or y prime, and then sub in 1, 1 in this case since it's implicitly. So here's our original function. And I've got it on Desmos so we can see what it looks like here. So it's an ellipse, okay? And you can see the point 1, 1 is here, so we're going to be expecting a negative slope of the tangent. So the derivative of 2x squared with respect to x is 4x. The derivative of 3y squared with respect to x is going to be 6y times dy by dx. And the derivative of 5 with respect to x is 0. And then divide both sides by 6y. So the slope of the tangent is negative 4x over 6y. Or you might say, I really want to divide top and bottom by 2 and get negative 2x over 3y. That's at any point, but we want to find it specifically at the point 1, 1. So we want the slope of the tangent at the point 1, 1. So that's x being 1, y being 1. In this case, it doesn't matter because they're both 1, but sometimes make sure you substitute them into the right spots in the equation. So negative 2 times 1 over 3 times 1 is negative 2/3. I'll write m tangent here. So therefore, m tangent is negative 2/3, which makes sense to our picture here. There's 1, 1. The tangent is negative. And you would go down 2 and over 3. Yep, that makes sense. Up 2 and over 3. That looks like it would be the tangent. Nice. Any questions about that one? Okay. The next one's a little trickier. We're still finding the slope of the tangent to a curve at a point. I can type this one into Desmos and see what it looks like. So x plus y cubed equals x cubed plus y cubed. That's interesting. Well, let's see what we get. Definitely not a function. Okay. Any ideas how you would derive x plus y all cubed? Can you hear me?
Yep.
Yeah. Okay.
I think you could do the chain rule, right?
Yes. So the 3 comes down. X plus y all squared times the inner derivative, which I could put in square brackets. So the derivative of x is 1, and the derivative of y is dy by dx. Okay? So that's this side. And then on the other side, the derivative of x cubed is 3x squared. And the derivative of y cubed is 3y squared times dy by dx. So then what you need to see here in order to get dy by dx by itself, because we see it here and here on this side and here on this side, is that we can use the distributive property to expand this bracket here and multiply each of these pieces by what's out front. So I've got 3 times x plus y squared times 1 is just 3 times x plus y squared. And then 3 times x plus y squared times dy by dx is 3 times x plus y squared dy by dx. So now we can see that this time we have dy by dx on 2 different sides of the equation, and we want to get them to be on the same side. So I'm going to subtract 3y squared dy by dx on both sides. So those are gone. And I've got 3 times x plus y squared plus 3x plus y squared times dy by dx minus 3y squared times dy by dx equals 3x squared. And then I also want to get this 3x plus y squared off of the left side, so I'm going to subtract it on both sides. So now on the right side, I've got 3x squared minus 3 times x plus y squared. And each chunk that I have on the left side has a dy by dx in it that I can common factor out. So I can common factor out dy by dx and get inside 3 times x plus y squared minus 3y squared. And then I can divide that on both sides. And that gives me dy by dx. But I want to find the slope of the tangent at the point negative 1, 1. So I'm going to come up here and write small. So dy by dx at the point negative 1, positive 1 is equal to 3 times negative 1 squared minus 3 times negative 1 plus 1, which makes 0, so that's nice, over 3 times negative 1 plus 1 squared minus 3 times 1 squared. So negative 1 plus 1 is 0. So 0 times anything is 0, so that term's gone. And likewise in the bottom, negative 1 plus 1 is 0. 0 times 3 is 0, so that term's gone. So I'm left with 3 times negative 1 squared, which is 3, over negative 3 times 1 squared, which is negative 3. So therefore, m tangent is negative 1 at the point negative 1, 1. Okay, so that's probably the most challenging one we've had so far, because it involved the chain rule and implicit differentiation together.
Ms. Notebook?
Yep.
I'm wondering, would we be able to say simplify, like expand out the x plus y cubed at the beginning? So then, and then like cancel out the x cubed and y cubed terms?
You could do that, yes.
Yeah?
Yeah.
All right.
How do you expand that one out? Just FOIL, or do you use Pascal's triangle?
Yeah, the Pascal's triangle sort of form, yeah.
Yep, for sure, John. Yeah, you could definitely do that. Okay, our last one for this morning. This afternoon is just more of these types of examples. We have like root x plus root y equals something. So just some different examples that are maybe a little bit more challenging, but same lines, similar. So find the equation of the tangent line to that curve at the point 4, 2. So if I started out by just writing out the equation and then putting my line to start deriving, derivative of x cubed is 3x squared, but then I would want you to realize right away that minus 6xy involves the product rule. So then I would make my chart. So my first is negative 6x, okay? My second is y. The derivative of the first is negative 6, and the derivative of the second is dy by dx. Okay, so we've derived the x cubed. Now we're deriving the negative 6xy. So derivative of the first times the second is negative 6y. Plus the first times the derivative of the second is negative 6x times dy by dx. And then the derivative of negative 2y cubed. So first derive that with respect to y, so that's going to be negative 6y squared, and then times dy by dx equals 0. And I'm noticing that where my dy by dx terms are, the terms that are multiplying the dy by dx are both negative. So I think I'm going to add them to the right side rather than leave them on the left side. That's probably what I'd do since they're both negative. So I'm going to add 6x dy by dx to each side. Oops, 6x dy by dx. And I'm also going to add 6y squared dy by dx to both sides. So on the left side, I've got the 3x squared minus 6y. And on the right side, I've got 6x dy by dx plus 6y squared dy by dx. I just, when I have a choice, I like to have positive signs, but still same answer, it's up to you. Simplifying isn't a big deal for implicit differentiation. So I still want to, on the right side, common factor out dy by dx, because that's my slope of the tangent. So I would get 6x plus 6y squared. And then to get dy by dx by itself, I'm going to divide both sides by 6x plus 6y squared. So that means that the slope of the, or dy by dx, the derivative, or the slope of the tangent, can be given by the formula 3x squared minus 6y over 6x plus 6y squared. Oh, I guess I don't need brackets anymore. Bottom. But we want it at the specific point 4, 2. So dy by dx at the point 4, 2, which means x is 4 and y is 2, is going to be 3 times 4 squared minus 6 times 2 over 6 times 4 plus 6 times 2 squared. Which is, so that's 48 minus 12 over 24 plus 24, which is 36 over 48. That reduces, 12 goes into both of them. So therefore, M tangent is going to be 3 over 4. Oh, they want the equation of the tangent line, though. I'm glad I looked back there. Equation of the tangent line. So that's our slope. We also know our point is 4, 2. So we can use y equals mx plus b to find the b value. So y equals mx plus b. 2 equals 3/4 times 4 plus b. 3/4 times 4 is just 3. So b is -1. So the equation of the tangent line would be y equals 3/4 x minus 1. I'm going to see if this one works when I put it in Desmos. See if I can show you a picture of the equation and the tangent line drawn in. X cubed minus 6xy minus 2y cubed equals 0. Look at what it looks like. It's got this little loop. And we want to know, so that's what it looks like. Kind of neat. And we want to know what the point 4, 2. So if I drag back so that we can see where 4, 2 is. Wait, 4, 2. Here we go. So 1, 2, 3, 4, 2. And then we'll type in our equation of our tangent line, which was y equals 3 over 4x minus 1. It should look tangent to the curve at 4, 2, so just touching it at that spot and resembling the slope of the curve. 1, 2, 3, 4, 2, yep. So that's our correct tangent line. Any questions for that one? So I've got a sheet with some questions and I'll post solutions. I'll get out of this now. I'll just talk to you, see if there's any questions about anything. So I want to stop recording.